Assalamu alaikum. Today we'll start chapter number 27 of Survey and Youth. This chapter covers a topic related to current and resistance. First article is related to electric current, and within this article I'll be covering 27.2 as well. चूँकि वो उसी की कंटिन्यूएशन में जो है जब हम ड्रिफ्ट वेलोसिटी और सब कैलकुलेट करेंगे तो उसके साथ ही वी विल बी कैलकुलेटिंग रेजिस्टेंस सो this is a combination, this lecture is a combination of article 27.1 as well as 27.2. So let's start with electric current. When we say what a current is, so normally it comes to our mind that it is the flow of electrons that produces current. But by convention, the definition of current is the flow of positive charges. The current is basically defined as when positive charges move in certain direction, then we say that the current is flowing. But in actual, the electrons they move and they comprise current. But by convention and by definition, it is said that it is the movement of positive charges. So when we apply a certain potential to a device or a circuit, the electric field it is produced, and when the electric field is created in the conductor, there are free electrons in that conductor, and these electrons are mobile, and ions they are not mobile, they are fixed or frozen in the solid or into the crystal. So basically the movement is due to the electrons, and the positive ions they are fixed in the crystal or in the material that we are taking as a conductor. So when the current flows in a conductor, it's always the electrons that are responsible for current. The electrons feel the electric field. Whenever we apply an electric field, it is felt by the electrons, and these electrons will try to make the electric field zero, but they cannot succeed. Why they cannot succeed? It is because we are continuously providing a potential difference across the circuit over the conductor. So because of the potential difference, the electron cannot make the field zero, and they will keep on experiencing a force, and they will keep on moving, and we will get current within the circuit. Usually there is a linear relationship between current and the potential, which will lead us to Ohm's law, which we will see later in the article. So the linear, just remember that the relationship between current and potential, it will be a linear relationship. So now what we will do, we will consider a conductor. Let that conductor be copper. We have a copper wire at room temperature, and mostly room temperature is considered to be 27 degrees Celsius, or in Kelvins it is 300 Kelvin. The average speed of electrons in copper is 10 raised to the power 6 meter per second. It is when we have not applied any potential to it. So when we have not applied any potential to it, the average speed of the electrons within that conductor is 10 raised to the power 6 meters per second, and this is because of the thermal agitation. All the electrons they are moving randomly within the conductor, and they are moving so fast that the speed is given to be 10 raised to the power 6 meters per second. So when they are moving, they obviously they will collide with one another, and the time between collision of these free electrons is 3 into 10 raised to the power minus 14 second, and this relaxation time, or the time between the collision, is usually represented by tau. So when we will talk about tau later, this means that we are talking about the time between the collision of these free electron. So that time is 3 into 10 to the power minus 14 second, and the number of free electrons in copper per cubic meter is 10 raised to the power 29. So we have 10 raised to the power 29 free electrons in copper per cubic meter. That is one free electrons for every atom. Now, if we apply potential difference, so remember one thing, that whatever we have said right now about the speed and the relaxation time, it is before applying potential. Now we have applied potential to this piece of copper. So obviously now the electrons, they will experience a force, and this force will be F is equal to QE. This Q is can be written as E, representing that the electrons, they are experiencing a force over here. So F is equal to E into capital E. Capital E is for electric field. Now because of the presence of the potential difference, the electrons, they will start moving, and the force and the electric field are in the opposite direction, because the electrons, they will experience a force in the opposite direction, that of the applied field. Now the electrons will experience acceleration, and from Newton's second law we know that F is equals to ma, where this m is mass of the electron. So I may write A is equal to F over me, and from this equation up over here, I can replace force in this equation. So I'll get acceleration equals to E, capital E, divided by me. So now the electrons attain a drift velocity, that is Vd equals to a tau. Vd is for drift velocity, a is for acceleration, and tau is the relaxation time. So we can write the same equation in the form of Vd equals to E, capital E over me into tau. So if we want to calculate drift velocity, either if we have relaxation time and acceleration of the electrons, we can calculate using this formula. But if additional information is given, that is the charge on electron or electric field, mass of electron, then we can use this equation to calculate our drift velocity, that is Vd is equal to E, capital E over me into tau. Therefore, if the electric field, from this relationship we can see that if the electric field, it goes up, the drift velocity will increase, and there is a direct relationship between the drift velocity and the electric field. And also, if the time between collision, it increases, the drift velocity will increase, because if an electron is having a greater time when it comes to collide with another particle, then obviously between that time it may accelerate more, and the drift velocity will increase more. So if tau is greater, then obviously the drift velocity will have a greater value. So these two parameters, because we know that E and me, they are the constants. So Vd is directly proportional to electric field, and drift velocity is directly proportional to the relaxation time. So if both of these parameters, they go up, the drift velocity will increase. So now I give a number to these parameters, and we'll see that what happens to the electrons when we have applied potential across the copper wire. So now reconsidering that copper wire which we have discussed earlier, so let us suppose that the length of the copper wire be 10 meters and we apply a potential of 10 volts to it. So if I want to find electric field, the value of electric field, I will simply use this formula, that is E is equal to V over D, and V is 10 and the length of the wire is also 10. So I'll get 1 volt per meter. So now I have the value of E, which is 1 volts per meter. If I put this value in this VD, so I know small e, I know capital E, I know the relaxation time, and I know the mass of electron. So by putting these values in the equation, I get this, that is 5.27 into 10 raised to the power minus 3 meters per second, or 0.5 centimeters per second. That is after applying the potential. The electrons, the drift velocity of the electrons is half centimeter per second, which is very slow uh, as compared to the one which they were experiencing when no potential was applied across it. So the drift velocity of the electrons due to thermal agitation was much greater than the drift velocity of the electrons after applying potential. So when electric field is applied, then they only advance along the wire so slow that it is even slower than a snail or a turtle. So therefore, if an electron is to go along 10-meter wire, it would take half an hour to move from one end to another end. So it seems quite slow as compared to the motion of the drift velocity of the electrons when there was no potential applied to it. So this is what happens to the electrons in a circuit when there is a potential and when there is no potential. Now from this point onwards, article 27.2, that is how to find the resistance, will start, and before going into detail, we will first discuss the figure given over here. Now considering a wire, the figure is, suppose this is the wire, this is a wire, let the L be the length of the wire, A is the area of this wire, the drift velocity of electron is in this direction, whereas current and electric field are in this direction, and the potential applied is V plus here and minus here. So the potential is applied across the wire. We know that E is equal to V over L or D. So we know how to calculate E. Also, if I consider this small section over here, and I say that D is equal to VDT, so the distance that the electron will travel from this point to this point be D equals to VDT. This is from the formula that we have, velocity is equal to displacement over time. So I'll say that the electron will travel from here to here in 1 second. So this D will be equal to Vd. So the drift velocity is equal to the distance traveled by electron in 1 second from here to here. So these are the parameters, that is, A is the area, L is the length of the wire, I is the current, V potential difference, E is electric field, and E is the charge on electron. So in a second, these free electrons will move from left to right over a distance Vd meters, which I have explained, that is in a second, the electrons they will move from this point to this point, and this distance is given as d is equal to drift velocity into time. As the time is 1 second, so this distance will be equal to your vd. So and this is what is given over here. So now the volume will be, the total volume will be vd into a, as vd is equals to d over here. Actually it is into t. This t is equals to 1, so this is equal to vd equals to d. So for volume, if d is equals to vd, then I may write it as vd into a. So the volume is in this case is vd into a, where small n is the number of free electrons per cubic meter. So number of electrons that passes through certain cross-sectional area. So the number of electrons that are passing through certain cross-section area will be n a into vd. So now each electron has charge e, and obviously these are the number of electrons crossing through certain area. So and each of these have charge e, so I may write the current equals to NAVD into E. So this whole thing is equals to my current. So usually we have seen the formula to calculate current is I equals to Q over T, that is the rate of flow of charges. We define it as current, but this is a different formula to calculate current. So if we have number of electrons in certain cross-sectional area with charge E on them, we can also calculate current in if we have these parameters with us. So the direction of the current is from positive to negative, which again in this case is not that important right now, because we are interested in knowing how to calculate current. So substituting vd, now I know the value of vd, I can substitute the value of vd over here, and I can again rewrite this equation 2 over here, that is n a e n a and this e, and then vd, I knew that vd is equal to small e into capital E tau over me. So this e and this e, they will multiply to give a square, so I have n a e square e tau over me. So this is another form of an equation to find current. So either we can find current using this formula or this formula or this formula. So all these give us current in amperes. Okay, if now I simply want to simplify this equation, uh, this is sigma, and this sigma is known as conductivity. It's a constant value. And in this equation, equation number 3, E square n tau over me, all these values are constant, and I by combining them together, I get sigma, and sigma is conductivity. Conductivity varies from material to material. Every material is associated with a certain value of conductivity. So this value depends upon the number of electrons, their relaxation time. Again, from material to material, this value of conductivity will vary. So I can replace this sigma in equation number 3, and I get I equals to sigma A E. So now from this equation, if I want to increase my current, I can have larger value of current with greater area. And again, if I want I have larger value for current, I can increase the value of electric field. So these two quantities will give me a greater value of current. So again, equation number 4 shows another way of representing current I, that is in amperes. So now we'll give some values and try to see what happens if I have certain values and I use these formulas which I have calculated above. So conductivity of copper at room temperature is easily calculated as we have all the parameters with us. So sigma in case of copper is 10 raised to the power 8 mho. This is the unit for conductivity. It is also written as this ohm meter raised to the power minus 1. So either you can write mho or you can write ohm meter raised to the power minus 1. Also, we know that E is equal to V over L, and I can write sigma A E and I can replace this E with V over L. So I have I equals to sigma A V over L, and from here I have simply taken this to one side and all of these to the other side. So V is equal to IL over A into 1 over sigma. This, the values within this bracket gives me R, that is the resistance. So L over A into sigma gives me resistance, and now I have V is equal to IR, which is most commonly known as Ohm's law. So starting with a simple copper wire and defining its different parameters and replacing one with another, finally we arrive to this form, which gives me Ohm's law. So equation 5 is V is equal to IR. Now sigma is equal to 1 over rho, and this 1 over rho is also known as resistivity, and its unit is ohm meters because it's the reciprocal of conductivity. So unit of conductivity is ohm meter raised to power minus 1, and the unit of resistivity will be ohms meter. And when I want to write this R equals to L over sigma A in the form of resistivity, I can write it as rho L over A. So both of these are correct. So in some of the problems, if conductivity is given, you can easily find the value of R using this formula, and in some cases if resistivity is given, then you can easily find value of resistance using rho L over A. So resistance is proportional to length of the wire. So longer the length of the wire, greater will be the resistance, because over the time the electrons, they will experience more resistance to the wire. And if we have greater area of the wire, then the resistance will be smaller, because think of something like a water pipe. So if we have a small water pipe, the water will experience more resistance if the area of the pipe is smaller and the length of the pipe is too much, then the water will experience more resistance. But if the area is bigger, larger, and we have smaller length, then the resistance will be smaller in this case. So resistance is directly proportional to the length and is inversely proportional to the area of the material that we are using. Ohm's law also holds for insulators. In next few minutes we'll see that how this helps us in finding a good conductor and a good insulator. So considering a material with area 10 raised to the power minus 6 meter square and its length equals to 1 meter, for good conductor, let us suppose that as we have discussed for copper, sigma is equal to 10 raised to the power 8 mho. So obviously it's a reciprocal, resistivity is its reciprocal, so the value of resistivity will be 10 raised to the power minus 8 ohms meter. Radius, resistance, from this formula I can easily calculate resistance using this formula, and resistance for a good conductor is R equals to 10 to the power minus 2 ohms. Now for good insulators, the value of sigma is 10 to the power minus 14 mho. So its resistivity will be 10 raised to the power 14 ohms meter. And if I put this value in this formula over here, the resistance will be 10 raised to the power 20 ohms. So there is the resistance is order of 22 magnitude greater for good conductor, lesser than for good conductor rather than for insulator. So insulators have very much higher value for resistance as compared to the resistance we have found for good conductors. For both of these we have selected area 10 raised to the power minus 6 and length equals to 1 meter. So now if we have 1 volt, then calculate the current through these materials. So again, if 1 volt is applied across these two, good conductor and good insulator, then the current will be I equals to V over R. So V is 1, R for good conductor was 10 raised to the power minus 2. So the current will be 100 amperes. For good insulator, R was 10 raised to the power 20 and voltage is 1. So the current will be 10 raised to the power minus 20 ampere, which is insignificant. So this is very small, negligible amount of current. Through good insulators we have no current or very small current, and in case of good conductors we have a very large amount of current which can flow through them. So we can also define current as rate at which the charges flow through the surface area. So this is what I have told you before, that this is what we have learned in our school days, that current is rate of flow of charges, that is charges per unit time when they pass through certain area. So we call it current. So I is defined as dq over dt, and the unit of current is amperes. So we can also write this I equals to dq over dt, which is also equals to nqvda. So these are the different forms through which we can represent our current. So from the same formula, now from this same formula I can find another very important parameter, and that is the current density. So current density is represented by J, and it is defined as current per unit area and is equals to nqvd. So from this equation over here we can find our current density, that is J equals to I over A equals to nqvd, and this may also be written as J equals to sigma E. So this J is directly proportional to the electric field, and sigma is a constant over here. Basically, this is what is Ohm's law is. This is Ohm's law, and this tells us about the relationship between the current density and the electric field. So, if someone asks that what Ohm's law is, so it is better to define Ohm's law is that current density is directly proportional to electric field, and it gives a linear relation, and sigma is a constant over here. So for many materials, the ratio of the current density to electric field is a constant, that is sigma. That is independent of the electric field producing current. There are two types of devices, that is ohmic and non-ohmic devices. When we talk about ohmic devices, we'll see that the relation between voltage and current, it's a linear relation, and the slope is 1 over r. But for non-ohmic devices, we'll get this exponential increase, and usually we have seen this thing in diodes. So these are the this is how graphically ohmic devices are represented, and this is how non-ohmic devices are shown. So from the above article, some important points that you must know is that the term current flow is incorrect because it is flow of charges that produces the current. Current itself does not flow, it is the charges that flow. So, and second one is a battery does not provide electrons to the circuit. It only establishes electric field that exerts a force on electrons already in the wire and elements of the circuit. So if someone has a concept that when we connect some circuit to a battery, then we'll get electrons in the circuit. So no, it's not correct, because battery only provides the electric field, which then exerts force on the electrons already present in the conductor or the circuit. And thirdly, the resistors have two common types, that is, one is composition resistors. They contain carbon in them, and the second one is wire wound resistors. They have coil of wire in them. So this is all about current and resistors. I hope you'll understand.